This is the third part of class on May 20th, May 15th, 2020. And this had to do with what's involved, what's actually in the flask while titration's going on. So visualize the flask. Remember the lady from Wits University in South Africa had the flask, and she had a burette sitting up on the top, and she was putting base, NaOH, that was in the burette. She put it into this flask, and in the flask there was HCl. Then I have another graph down here. We have the same setup going on, except this has got acetic acid in it. So this one is NaOH with acetic acid. We can write it like that. Okay. So I have some images over here on the left side, which are of different titrations. I thought I'd just point out. Like this one is an HCl titration. Notice that if you compare this blue line to this blue line down here, see the difference in the way the curve looks? And this is one that I actually did one day. And you see how the curve looks a little, not quite as dramatic as this one, but it goes up like that, then it flatlines a little bit. Whereas the HCl is a little more just continuously flat and comes around all of a sudden and goes up. Now remember we talked about titrations at the point where when you reach the what's called the equivalence point, that is this point here, that's the midpoint of the region of steepest slope. And that at this point where I'm pointing, the acid is completely gone. And the base is you've added just enough of the sodium hydroxide to neutralize it. Now as you keep going, then the pH continues to go up because you're adding NaOH. And the reason you keep going is because you want to get a nice line, vertical line here, so you can find the equivalence point. All right, these are both NaOH and HCl. You see the lines look pretty similar. Okay, but the acetic acid is quite a bit different. So I wanted to talk about what's in a solution at the beginning, kind of at the midpoint, and then over here at the equivalence point, and then at the end, just to develop a mental image of kind of what happens chemically. So at the beginning, we had only, in this case, only the unionized acid, HC2H3O2, but really there's a lot of that, and there's just a little bit of these hydronium ions and the acetate ions. And of course there's water in every case. I left that out. So you've got a lot of these and a little bit of that. Now the chemical reaction is HC2H3O2 plus NaOH. So as you proceed, you're going to be forming sodium acetate and water. So all along this line, you're getting less and less of this unionized acid and more of this sodium acetate until you get all over this point. And at this point, and by the way, notice the pH here is not 7. So at this point, you have sodium ions and acetate ions floating around independently of each other in the solution. However, the acetate ions are actually reacting a little bit with the water. Remember, we just in part 2 talked about that? So these acetate ions react with the water, and they make just a little bit of HC2H3O2 and hydroxide ions. And it's these hydroxide ions that cause the pH to be just slightly above 7. Now, along the way, I suppose you're right here. This is a key point in chemistry. It's called the halfway points, halfway from the beginning to the equivalence point. All right, now I might not have it exactly halfway, but the halfway points just make a bigger dot. So the halfway point is when you're halfway to the equivalence point. At that point, you've got some unreacted acid, and that unreacted acid is still in equilibrium like this. I'm going to just write this out. And you also have some sodium acetate. The sodium acetate, though, doesn't stay together. It comes apart as sodium ions and acetate ions. Now, I want you to notice that these ions and these ions are the same. So we started with a lot of this, but hardly any of these. But as we moved on, we've had a growth, so to speak, of these acetate ions. So that creates what's called the common ion effect. The common ion effect. And it creates what we call a buffer system. And then in this class, I didn't get into exactly how a buffer system works, but I do want you to know that as you create a buffer system, a buffer is something that allows you to add a certain amount of acid or a certain amount of base, either one, without having a significant change in the pH. And it's created by having a weak acid and the anion of the weak acid. You need to have a lot of both of these relative to each other. And as this reaction proceeds, it gradually turns into a buffer system where this ion will cause this equilibrium to shift and push it back that way, causing this to go down a little bit, which makes it less acidic than you would expect it to be. All right, so that's what's in the solution as you go through. I wanted you to know at the beginning, you just have the acid that determines the pH. At the end, all you have is a salt, and it's the hydrolysis that determines the pH at that point. And along the way, it's this acid in combination with the salt that is being produced that affects the pH, because it's not just this, the H3O is different than it would be if you just had the acid by itself, because you have this additional salt. Now, that's not as true in HCl, because if you look over at the HCl, what happens is at this point you've got same thing, you got HCl, and but there is no HCl in an HCl solution because HCl is a strong acid. So HCl does this, single arrow. And there is no common ion effect because there's no equilibrium here. So HCl doesn't have an equilibrium to be shifted by the formation of the chloride ions. You still are having, at that halfway point on the HCl, you'd still have that. You'd have a lot of these, but you wouldn't have any of these because there's no equilibrium. So whatever HCl you have, it all comes apart like that. So at the midpoint on this, at the halfway point on the graph with the HCl, it's a little different than it is over here because at this halfway point you have unreacted acid, and at this one you don't have any unionized acid. It's all ionized, 100%. All right, and that's, I kind of left you hanging on the buffers in class today, and I think I'll probably leave you hanging for the year in class today on what happens on how buffer systems work. So if you'd like to know more about those, you have to do the AP class. All right, so I'm going to stop this video at this point, but to just quickly summarize, I want you to know there's a lot of acid over here that's unreacted, and over here, and that determines the pH. Along the way, the pH is determined by the acid, the ionization of this acid, but also affected by the common ion effect, shifting this equilibrium. So there's an equilibrium that's being shifted. With HCl, there is no equilibrium because HCl is a strong acid, comes apart. And then when you get to the end, the ion from the weak thing hydrolyzes, and that reacts with water and creates OHs in this case, which causes the pH to be above 7. In the HCl graph, notice that there is no ion from the weak thing because in NaCl, the Na came from a strong base and Cl came from a strong acid, so that strong pH should be 7. And if you look over here, this is the equivalence point. It's the easiest one to see. See, that pH is right there at 7. All right, so a little bit more background on what is going on in the flasks as the titration proceeds. And I didn't say anything about the far end over here. Up on this side, you have sodium ions, and you have hydroxide ions, because at this point there aren't any hydroxide because they all got turned into water. But once you pass this point, you're just adding hydroxides. And then you still have the acetate ions that are over here. All right. So I'll end it there.